In lecture B, we're going to go through a topic called Fourier series, especially focus on something called Fourier polynomials. They're not really polynomials, though. That's why I'm putting the word polynomials in quotes. Before we do that, though, I want to look at some Mathematica stuff. And oh, I forgot to test the sound system ahead of time here. You can get Mathematica to play things for you, sound waves, with the code that you see there. Let's see, is the... Oh, I should have tested this ahead of time. I'm not sure if the sound system is turned on. Let's just check it and see if it is. There we go, it is. I don't know how to turn it down, though. That's kind of loud.
There's that little keyboard thing right next to, no, up above.
This
that
thing?
there, as above.
That's for the projector, I think.
That controls everything. So yeah.
Okay, you think it controls sound here? Okay,
Does it
try
not?
it. Okay, it does. Thanks. What is that? That's a pure sound wave of frequency. Well, it says 8,000 hertz here, though. So maybe it's, that seems too high. I think it's supposed to be 440 cycles per second, hertz. Is supposed to be the frequency. I think that's too high to barely even hear. So I think that must be wrong. I think it must be the 440 here. I copied and pasted this code from the documentation center. So that's a sound, a pure tone. You can combine tones, though. Look, we've got a sum of sine functions, one of frequency 440 hertz and one double the frequency 880. So you should really hear two tones in this, though unless if you got a bad ear, maybe you can't. I think I can hear two tones in that. One double the frequency of the other. On like a piano, that would correspond to one being one octave above the other. Is 440 hertz like middle C or something? Does anybody know? You think it is? Okay. Here I've got three tones, the last one being double the second one there. Here, the 550 hertz is not an integer multiple of 440, though I think this still does produce a nice sound, I think. That's still kind of a nice sound. But the two tones you're hearing are not the same note in that case. They don't differ by an octave. And here I purposely made one where the frequency is only slightly different. We don't really hear dissonance so much as it's called a beating pattern when you combine those kinds of waves. Can we hear something dissonant? Probably if we, let's see, make this one, I don't know, be a 473 or something. That'll probably sound dissonant. Yeah, that's so good. That's such a pretty sound that time. So you can use Mathematica to make sound waves essentially based on the formula you plug in. How is that relevant for what we're about to talk about? Well, Fourier series is a way of decomposing periodic functions in terms of sines and cosines. We're approximating periodic functions in terms of sines and cosines, which are periodic. But these periodic functions that we're approximating could be very complicated, and the book discusses examples like that. Or they could be fairly simple, but kind of oddball, you might say, like, what's this graph here? Triangle wave is a built-in Mathematica function that produces a graph that looks like that. Is it possible a sound wave could look like that? Well, you can actually have Mathematica play that sound wave, although by putting I want to increase the frequency, and I did that then here in the play by not having the input be x, but 2 pi times 440x. So we're about to listen to a sound with a frequency of 440 hertz But it's not really so much of a pure sinusoidal function, so it might sound a little funny, I'm not sure. So yeah, that's a little odd maybe. That's what a triangular sound wave sounds like. You might wonder, since it is kind of an odd sound, though it's coming through overall at 440 hertz, are there overtones? Are there sort of frequencies other than the 440 hertz that are kind of hidden in this triangular wave? And that's the question Fourier series are designed to answer. What is a Fourier series in general? It's an expression of the following form: some constant A0 plus an infinite sum, k going from 1 to infinity, of the following form. It's not a power series. You're not adding up multiples of x to the k power. Instead, you're adding up multiples of cosines and sines with different frequencies. A sub k times cosine of kx plus b sub k times sine of bx. That's a Taylor series. It is an infinite series. Hmm?
So are we talking about Fourier series now?
Yeah, sorry. Why did I say Taylor? Fourier. Did I say Taylor earlier too? No. Okay. My mind was on Taylor series. I meant Fourier series. This is a Fourier series that is an infinite sum. And remember, we've said infinite sums are not literally sums. They're really limits of partial sums. The partial sum is called a Fourier polynomial. Essentially, it's the same kind of thing, except replace the infinity with an n. That's a finite sum, so there's no problem with defining this for any x. But then you wonder, what happens to this as n goes to infinity? Does it converge or not? If it does converge, you write the thing it converges to in symbolic form like this, the Fourier series, and put infinity up there. So as an idea, it's just a constant, which is sort of like the vertical shift of whatever your graph is, plus a combination of cosines and sines of different frequencies. The different k's give you different frequencies. Mm-hmm.
In the Fourier series, is it supposed to be plus sine of kx? Like on the board? Instead of bx?
Yeah, kx, thank you. Sorry about that. Mistakes here. This is supposed to be a kx. There are formulas for these coefficients. These formulas are kind of complicated because the formulas for the a's and b's involve integrals. Turns out that a0 is the average value of the function that you are approximating over the interval from negative pi to positive pi. That interval has length 2 pi, so it's 1 over 2 pi times the integral from negative pi to pi of the function we are trying to approximate. That's what a0 is. ak, for an arbitrary positive integer k, 1, 2, 3, 4, 5, 6, etc., is also found by an integral.
I have a question.
Mm-hmm.
So why the 1 over 2 pi and the negative pi to pi? Is that because of the cosine?
It's because of the periodicity. We're trying to approximate periodic functions. Good question.
So is that just the general formula then?
This is the formula for approximating functions that are periodic with period 2 pi, which, plain cosines and sines are period 2 pi.
Would it be the same thing if you did 0 to
0 to 2 pi would give you the same answer. Yep. Good questions. Turns out that ak is 1 over pi, not 1 over 2 pi, for reasons I'm not going to get into, times the integral from negative pi to pi of the function f of x times cosine of k times x. Okay there. And bk is a similar integral, except replace the cosine with the sine. 1 over pi times the integral from negative pi to pi of the function we're trying to approximate times the sine of kx. In general, these integrals can be very tricky to do. For a general example for f of x. But for certain special cases, they're not too bad to do. And oftentimes you can use symmetry. Maybe a function is odd, for example, and then the integral ends up being 0 because it's an odd function. Or maybe the function you're integrating is even, and you can do the integral just from 0 to pi and double it to help you find the whole integral if it's an even function. Sometimes that is the case. What would it be for this triangular wave? Actually, this is not the original triangular wave here. I'm taking x divided by 2 pi in the input. The reason I did that was to make this new triangular wave have a period 2 pi so that these formulas can be used. Does it really have period 2 pi? There's pi right there, negative pi, excuse me. It goes down, back up, and back down again to the same spot when you get to positive pi. This does have period 2 pi. So this is a function I can apply these formulas to try to get some Taylor polynomial approximation to this graph. Okay? I've programmed Mathematica to do this integral for the b's. But you can see it's kind of a mess because this function is piecewise, really. It's got one formula when x is between negative pi and negative pi over 2. Another formula for this piece of the graph when x is between negative pi over 2 and positive pi over 2. And another formula for this piece of the graph when x is between pi over 2 and pi. So to do it based on this formula here, you see the 1 over pi in front, I had to break the integral up into pieces. An integral from negative pi over 2, negative pi to negative pi over 2, from negative pi over 2 to positive pi over 2, and from positive pi over 2 to pi. You see a sign in each case. I guess I'm calling this bn instead of bk. That's all right. And then you see sine of x being multiplied by different things in each of these cases. Each of these things is a formula for this function over the different pieces. For example, this piece right there, 2 over pi times x, is a formula for this piece of the graph. That's a line, a straight line with a slope of 2 over pi, evidently, and an intercept of 0. Is the slope really 2 over pi? Yeah. Rise is going to be from here to here, goes up by 2. The run is from negative pi over 2 to positive pi over 2, which is pi units. 2 over pi is the slope of that line. It goes to the origin, so you multiply that by x. That's the formula for this piece of the graph. These other two formulas are formulas for the other two pieces of the graph. For example, this part has a slope of negative 2 over pi, and it goes to the point whose coordinates are negative pi 0. When you plug in x equals negative pi there, you get 0. This formula right down there is the formula for this piece of the graph. Slope of negative 2 over pi. It also goes to the point whose coordinates are pi comma 0. When you plug in x equals pi there, you get 0. Kind of a nasty computation to do by hand. Can you imagine doing this by hand? It'd be nasty. Probably the best thing to use is Mathematica, or if you had to try to use a table in the back of the book to help you do the integral. Are any of these formulas in this table relevant? Yeah, I think the most relevant ones are, if you look back there, 15 and 16. They're at the top of this page in the back of the book. But it'd be nasty, okay? So suffice it to say, I would not have you do one this hard of a test, okay? Because it would be a nasty integral to do by hand. But Mathematica can do it. And then Mathematica can evaluate these b's for different n's, like n equals 3, for example. It's negative 8 over 9 pi squared. That's b3. What about the a's? I don't have any a's in there. Why not? It's because for the formula for the a's, this function times cosine is going to be an odd function, actually. and therefore this integral is going to be 0. Why is it an odd function? Well, cosine is an even function. This function that we have, this triangle wave, is actually an odd function. It's got symmetry with respect to the origin. Its integral from negative pi to positive pi is 0. This integral would be 0 for sure. The product of an odd function times an even function turns out to be an odd function, which is, careful, it's not the same as it works with numbers, right? The product of an odd number times an even number is an even number. With functions, it's different though. An odd function times an even function is actually an odd function. If you graph this function, it would have origin symmetry like this one does. These integrals end up being 0. I mean, you could check it if you wanted to, but it would be 0. So with the Taylor series for this one, we only need the sine function. Excuse me, the Fourier series. The a's go away. And what you see here then is a Taylor polynomial of degree n for this function. And I guess I went to using k's as the index of summation here. That's okay. For example, what is the 20 degree Taylor polynomial approximation here? It's kind of long. It does only involve sines. There it is. There's a 20th degree Taylor polynomial approximation, Fourier polynomial approximation to the original graph. You saw the triangular wave. If you try to graph this thing though, and if you try to make it manipulate and change the value of n, it really bogs down a lot. So what I did down here is I identified the pattern in the coefficients. They all have an 8 up top. They all have a pi squared in the bottom. And they've got a perfect square that's the perfect square of an odd number as well. And their signs alternate, plus, minus, plus, minus. That allows me to plug in this formula that's going to give you the exact same answer, but Mathematica will compute it more quickly than trying to redo all the integrals from before. And we can see in animation that these blue graphs approximate the red graph better and better. The higher the degree of the Taylor polynomial is, if I keep stepping forward, I get better and better approximations to the red graph. What's the practical meaning of that? You know, why would you want to approximate this triangular wave with trig functions? Well, you can get into something called the energy spectrum of the function to identify what the major frequencies there are hidden in this triangular wave that you can't see just by looking at the picture. And that is related to the sound that it produces in our ears. I'm not going to get into the formula for the coefficients of the energy spectrum, but let me just point out that when you plot this energy spectrum, and the book does talk about it, with a triangular wave, what you see is a very high energy, so to speak, in what's called the first harmonic, which actually means it's a pretty pure tone. This triangular wave does make a pretty pure sound. There is a small amount of energy in the third harmonic. That would be the surprise, so to speak, that this is telling you. There's a small amount of energy in this triangular wave in the third harmonic compared to the second harmonic, for example. And that is related to the sound techniques. Details of that, you'd have to get into engineering and how your ears work or something. I take that at an intuitive level. It's a pretty pure tone, though there's a little bit of an overtone that is a frequency 3 times as much as the pure tone. What about a square wave? A square wave looks like that. What does it sound like when you increase its frequency overall to 440 hertz? It sounds like this. I don't know how different that is from the other one. That is an odd function as well, by the way. So if we find a Fourier series for it, it will only involve sines and no cosines. The b's will be non-zero, but not the a's. The a's will be 0. Once again, I'm having Mathematica compute the Fourier coefficients, the b's in this case. Notice what I'm doing here. This is a piecewise function. It's periodic at period 2 pi. This is the interval from negative pi to pi here. It's got one formula when x is between 0 and pi, and another formula when x is between negative pi and 0. In fact, it's negative 1 when you're between negative pi and 0, and positive 1 when you're between 0 and pi. This is the integral that will give you the values of the b's. Split into two parts because f of x has two different formulas depending on where you are. These integrals would actually not be too hard to do by hand. I could see this coming up on the test. Doing these integrals would be relatively easy. For example, the integral on the right, integral from 0 to pi integral from 0 to pi of sine of nx, that's going to be negative 1 over n cosine of nx evaluated from 0 to pi. Negative 1 over n times the cosine of n pi minus cosine of 0. Let's put those in parentheses. Cosine of 0 is 1, so that's always a 1. Cosine of n pi, n being a positive integer, 1, 2, 3, 4, 5, 6, etc., could be 1, it could be negative 1. It depends on whether n is even or odd. If n is odd, like cosine of pi, cosine of 3 pi, cosine of 5 pi, your angle's over here, the cosine is negative 1. Negative 1 minus 1 is negative 2. If n is even, 2, 4, 6, etc., your angle is the same as the angle for 0. Cosine of that angle is positive 1. 1 minus 1 is 0. So this cancels out to 0 when n is even. But it becomes a negative 2 when n is odd. And when you multiply that by negative 1 over n, you get positive 2 over n if n is odd, and 0 if n is even. You got to multiply by 1 over pi as well. You got to do this integral as well. But as far as that particular integral goes, there's how you can figure it out. Not too bad. Because our function is 1 or negative 1, that's what makes it simpler. What does the Fourier polynomial of degree 20, for example, look like? For this example, it looks like that. Do notice we only have odd coefficients for the x's, no even coefficients. I think for that other one we did get even coefficients, didn't we? For that other example? No, they were all odd there too. Okay. Only odd coefficients of the x. What does the graph look like? There's the Taylor polynomial of degree 1. Degree 2, I think should be the same perhaps, since, unless, based on the formula for how you get g there. Actually, it's going to be different. And this is actually degree 3. When n is 2. When n is 3, you're going to get degree 5, and it looks like this. When n is 4, you get degree 7, and it looks like that. And you have to wait for it to smooth itself out a little bit. It's doing a lot of calculations. Etc. The bigger n is, the bigger the approximation to the square wave is, the better the approximation is overall. I mean, it still doesn't do real well near individual points, like near the end points of the graph. It doesn't do real well. But it does, roughly speaking, a pretty good job overall. Without, again, getting into details for the formula for the energy spectrum, what does the energy spectrum look like in this case? It looks like this, and this is surprising. This is telling you something new. It's telling you that in that square wave sound wave we heard a few minutes ago, certainly, again, most of the energy is in the main first harmonic. But there's a fair amount of energy in the third harmonic and the fifth harmonic, which this has 3 times the frequency, the main frequency. This has 5 times the main frequency. There's even a little bit of energy in the 7th and 9th, the odd harmonics, that is noticeable in this graph. That's a less pure sound. A square wave is a less pure sound than a triangular wave. That's the practical meaning of this. Okay? If you want to think, what practical meaning does this have for my life? If you appreciate music, okay, and you even appreciate odd sounds like square waves, it's good to know, I suppose, that there are more overtones, so to speak, in a square wave than there are in a triangular wave. If you're a musician, you might want to know that. Okay. Does it have practical meaning in other areas? Yes, it does. I'm just not an expert. I'm sure in electrical engineering it's useful to know these things. Communications, whether they be analog or digital, it's good to know this stuff. And it mostly applies to analog signals, but analogous things apply to digital signals. One more quick example. This one's called a sawtooth wave. It's triangular, except it's only one side of the triangle. What does that sound like? Maybe I should play these one right after the other so we can hear a difference. So you got that sound in your mind? This sound should be different. Yeah, it's different. That's the pure sound. That's the triangular wave. What do the coefficients for the sawtooth wave look like? What's the 20th degree Taylor polynomial? It's that involves some even coefficients of x as well for this one. Here's what the graph looks like. Step forward, you get better and better overall approximations to that sawtooth wave. And the energy spectrum, once again, shows you what kinds of harmonics are kind of hidden in that sound. Lots of them, actually. That sawtooth wave has a good amount of its energy in lots of different frequencies. Okay? So that's the basics. I'm giving you sort of a global picture of what Fourier series are about. As far as your homework goes, you'll be able to use Mathematica to do your calculations. Okay? And you can, like we did with the actuarial stuff, you can just write down what intervals you calculated, and then have Mathematica do the calculations for you. On the test, I've got to give you some help, just like I'm going to have to with the actuarial problems, to help avoid mistakes for one thing, but also to keep the problems relatively short. Okay? So somehow I'm going to have to construct problems where I basically tell you what to do, and you do it, like maybe do one of those intervals, essentially. Okay? And we'll talk more about the power, the energy stuff on Wednesday. We'll try to make more sense out of that, because I know I went over that very, very fast. But somehow I'm going to have to try to give you help with that, so that these are doable problems on the test. Okay? But for the moment, you're just using technology and trying to appreciate the formulas and the graphs and the sounds. Okay? See you on Wednesday.